Didn't work. I'm gonna do it. Oh. Now it takes forever. Can you step away, Rick? Did it work? Okay, good. Well, good morning. It's a great pleasure to be here with all of you. Am I too loud? I hear myself too loud. My email. All my secrets. Thank you. Well, I started out to say what a pleasure it is to be here with all of you in beautiful Catania. It's already been mentioned several times this week what the R process is, the rapid neutron capture process. We all know that it's responsible for over 50% of the elements heavier than iron. But the identification of the site of the R process, it is still one of the grand challenges in all of physics today. You might expect me, perhaps you will suspect that in this talk I'm not going to tell you where is the site of the R process, and you would be correct in that. But what I would like to tell you today is that we have forged a clear path to answering this question, where is the site of the R process? I hope I can convince you of that by the end of this talk. We're having many technical difficulties. Okay. So we nuclear physicists come in all different flavors, you know that. Not only are we experimentalists and theorists, but we're also have very different convictions about things in life. And one of the things that we've been doing, at least the experimental nuclear physicists have been doing, is running around building all kinds of radioactive ion beam facilities, not only building, but also running and making measurements. And often we're very excited when we measure a nucleus that's one neutron further away from stability, saying we measured something that's important for the R process. Well, then there's the others of us with convictions that we're never going to measure anything of the R process nuclei because the R process path is way too far, way too neutron rich. So these two questions actually are the reason or the motivation behind this work. We wanted to answer the question of, can we measure any nuclei important for the R process along the R process path? And if the answer to that is yes, then which ones should we measure first? There are thousands of them in the path, so which ones do we do first? Okay, so we know very well how to make nuclei or the elements beyond iron. We know that it has to be in a neutron-induced process of some kind. And we understand fairly well that we make the heavier ones by capturing more and more neutrons, and in order to get to very heavier things, we have to do successive neutron captures and then beta decays. And things that affect all of that are the capture rates or the beta delayed emission probabilities. So we know all of that. What we don't know is the conditions under which those parameters have to operate. So while we know the nuclear properties, we don't know the conditions under which we're going to apply those properties. So let's collect what we do know. What do we know? Well, we know that this is from a figure in Physics Today on radioactive beams by Henrik Schatz. Basically shows that the elemental distribution in the very oldest stars don't go beyond iron. We know that. We also know that elements beyond iron do exist. So this is the abundance distribution of our solar system. So in this abundance distribution is the entangled combined effect of the history of the universe, the nuclear physics, and the astrophysical conditions. So in principle, by understanding what we see in the abundance distributions, we can tell where the site of the R process is. So this is an approach that we took in this study, and I'll show you some things about that. There are other things we know. Astronomers have observed the elemental abundances in a large number of metal-poor stars. And the pattern is extremely robust. That means that the process that contributes to making the R process has to be universal, at least for the very heavier nuclei. So we're talking about normal R process beyond mass 120 or so. So where is the R process taking place? So I've put pictures up of the two favorite candidates at the moment. So core collapse supernovae or two neutron star mergers. What's important for the R process? That we have enough neutrons, we have high enough entropies, and we have the right kind of temperature and density variations as a function of time so that we get the abundances that are observed. Well, that was the approach that we took. What I show here on the inset in black is the abundances of the R process elements. So here, this is the solar abundances of the elements, subtracted away the S process abundances, and what's left behind is the R process abundance distributions. In principle, all we have to do is write the right conditions, the right trajectory for the different astrophysical sites, compare with the R process elemental distributions, and we have our site. The complication is that we don't know astrophysical models that well, and there are a large number of uncertainties, so we can say what happens in a two-neutron star merger. So we have a trajectory that describes what happens in a two-neutron star merger, but there are a number of uncertainties involved with that. What about the nuclear physics? Well, the nuclear physics, I love to show this plot. It's a fairly old one between the red and the purple here. Those show differences in nuclear physics models for masses. So there are uncertainties on the nuclear physics side, far from stability. So you have both sets of uncertainties that play into producing what we see as the R process abundance distributions. So this is what we have tried to disentangle. Our goal was to take the nuclear physics apart from the astrophysics and see if we can say, these are the nuclei we have to go after. Okay. Here are again the two potential R process sites. The two neutron star mergers or the core collapse supernovae. So people think the R process could have happened in the neutrino wind of the core collapse supernovae. So we basically took trajectories that describe 4 astrophysical scenarios, and then try to do a sensitivity study, both varying the nuclear physics part and the astrophysics part, to try and see what the effects are and where it takes us. Okay. Oh, I should say a few words about the trajectories. So there's one trajectory here that corresponds to the neutron-star merger. And there are 3 that have to do under various conditions of the neutrino wind from a core collapse supernova. In one case, it's a high entropy situation, low entropy. And what is called a cold-R process is really the neutrino wind that goes very fast out, and it's called cold, but it's really because the neutrinos are traveling very fast out. What's important about these different trajectories is that different nuclear physics parameters are important under these different conditions. And this is something we didn't know, because until now, all sensitivity studies addressed situations where you had equilibrium between n gamma and gamma n. And that only happens in high entropy, hot R process, or the traditional core collapse supernovae neutrino winds. In that case, you start out with an n gamma gamma n equilibrium. Then everything is determined basically by the masses and beta decay rates. But by taking these different trajectories and doing the kinds of simulations that we've done, we've let that free and let the equilibrium be determined by the astrophysical conditions. So here's our approach. It's heavily computational. And we started by looking at the R process abundance distributions and saying, we can determine individually, nucleus by nucleus, what the effect of a given nuclear parameter changes to the R process abundances. So I will take you through a brief trip of how we started and where we ended up. So what does our approach involve? I mentioned already that the equilibrium set point is not assumed ahead of time. So depending on the situation, you sometimes, for a cold R process, the equilibrium is set and escaped very early on. And in the hot R process, you stay in an equilibrium situation. If you stay in equilibrium, masses are the most important. If you fall out of equilibrium, neutron capture rates become important, or beta decay rates become important. Okay, so what did we do? We know what goes into our process simulations: masses, neutron capture rates, beta decay rates, beta delayed neutron emission probabilities. We took each of those parameters one by one for all the nuclei that may be involved in an R process. So we're talking about like 3,000, a little bit more than 3,000 calculations. And then vary that amount up and vary that amount down individually, compare it against a baseline, and identify the nuclei that have the largest impact on the abundance distributions. Pretty simple idea, a bit computationally intensive, but kind of a cute idea. Okay, how do we quantify that difference? And we did it by this F metric, which is just a basic comparison with a baseline for that change for a mass fraction of the abundance distribution. We initially started doing this for each parameter, as I said, and I'll give an example of the masses first. So we all know in the nuclear physics community how mass models vary where there are no measurements. So this is the point I'd like to demonstrate here, that using different mass models and what it tells us. So in this first set of simulations, we fixed the astrophysics and then tried to vary the nuclear physics. So we started out with various mass models, as we're familiar with. So took each of those theoretical masses for individual nuclei, raised it by 1 MeV, did a calculation compared against the baseline, decreased it by 1 MeV, did a calculation, compared it against the baseline, and identified a set of nuclei that have a big impact on the R process. Okay, what does that look like? Let me just show you that this is a plot of mass excess normalized to Peter Muller's finite range droplet model for a number of cadmium isotopes. We've all seen figures like this, where this is in a measured range. You have a ratio of 1, and away from measurement, you have these huge divergences of the order of several MeV. All right? So initially, we started off with this 1 MeV changes, plus or minus, for the cases where we don't have measurements. Of course, using the measured values where they exist. Here's the result for 3 mass models. This is the same astrophysics scenario, 3 different mass models. I'll take us back to the variations of these 3 models. I guess they're not exactly the same ones, but they are tremendously huge. And if you look, we're not doing well here. I turned it off. Okay, so take a look at these. So the intensity of color indicates the ones that have the biggest impact on the R process. So what you might notice is, in spite of the fact that these 3 mass models have very different nuclear physics, basically the same set of nuclei emerge as being important. So that was shock number 1 for us. It doesn't matter what nuclear physics models you use for masses, the same nuclei stand out as being important for the R process. Here is a compilation of masses, mass models against the recent compilation of measured masses, the AME 2012. And the only point of this figure is to show, you can see this is the finite range droplet model 1995 or the 2012. Those of you that heard Peter Muller speak on Monday, he mentioned that the root mean square value has improved. There are others, as you can see, and the RMS values are all about 500 to 700 keV. So making mass changes on the order of 1 MeV was totally reasonable, but perhaps more reasonable would be to do half of that, half an MeV. So this is what gave us the courage to go ahead and make these mass variations on the order of half an MeV, plus or minus. What's shown here is for, again, a hot R process trajectory for 3 different mass models, looking at the error that you get to the abundance distributions based on this half an MeV error assumption. And the broader color bands are that. This approach was developed by my postdoc, Matthew Mumpower. But we said, even in such a case, you have one astrophysical scenario and different mass models. What sort of RMS value do we need to be able to differentiate those? And the inner darker color is 100 keV. This should come as a shock for most people who work on mass models, because we don't have any mass models that are this precise. Okay. This figure here shows the result of, in this case, taking the same mass model and varying the astrophysical scenario. What's varied here is the entropy. So it's going from low to high entropy per baryon number for 3 different astrophysical scenarios in a core collapse supernova. And all I'm asking you to do is just look at the color variations, where the most important nuclei to measure are. I didn't say anything about the black line here. And this is sort of US-centric approach, because that's the number that FRIB thinks it's going to produce. That's the range of, or the limit of where measurements are possible. So the answer of, are the most important nuclei for the R process, are they measurable? It's yes, depending on the astrophysical scenario. And which ones are the most important depend on the astrophysical scenario that we choose. Let's go ahead. So I'll just summarize what we did for this individual property variations for, this is for neutron capture rates, for masses, for beta decay rates, and for beta delayed neutron emission probabilities. So this variation was done with 1 MeV binding energy change, the neutron capture rates by a factor of 100 up, 100 down, and beta decay rates by a factor of 10 up and 10 down. And the beta neutron, I'm just not getting the words out. In this case, so we turned it off. So the beta delayed neutron emission probability was either set to 0 or turned on. Where you see a concentration at the closed shells might be what you would expect. But depending on the astrophysics, again, this is a fixed astrophysical scenario, you get variations in the site. Okay? So all of these involved individual parameter variations, but we knew that that wasn't good enough, because if you make a change in mass, you affect all of the other related properties too. You affect the beta decays, the neutron capture rates, and depending on the astrophysical scenario, different parameters are important and come to play. So we tried to put it all together in a fully consistent way. So that means that if we change one mass, then it affects all the neighboring nuclei in terms of the beta delayed neutron emission probabilities, the separation energies, neutron capture rates, and the beta decay rates. So one mass change has all of these effects on the neighboring nuclei. So every time we made a mass change, now we propagated to all the values that are changed and did this individually for all 3,000 nuclei twice. Okay. What's the result? And I'll show you here in terms of the contribution of the different pieces. This is for tin 140. Obviously, picked one that has a big impact. So just want to show you the components and the effects of the different pieces here. The solid line here is the baseline calculation. This is the effect on the neutron capture rates, the beta decay rates. What's shown here is percentage difference. So you can see you have some fairly significant percentage differences, even though the calculation itself looks very close for the abundance distributions. Neutron separation energies, and adding it all up together. The point here is that you get an abundance distribution change that's an order of magnitude for a mass change that's half an MeV. What's the result for these 4 different trajectories? So I should mention that in all of these trajectories, particularly these results, we have used, Peter Muller was kind enough to share with us his latest mass model. We've often used the beta decay rates from his model because they're published. A lot of the other mass models don't have published beta decay rates, so a lot of what we've used has been that. So here, all of the nuclear physics is the same for these 4 trajectories. So a low entropy hot wind, a high entropy hot wind, a cold wind, and a neutron star merger. And again, you can see with intensity of color what the most important nuclei to measure are different, depending on the astrophysical scenarios. The low entropy hot wind is probably the one that we would have guessed without having done any calculations. And you can see the variations. You see for a cold wind, you have some nuclei far beyond where FRIB can reach that are important, but still there's a number near the closed shells. And then for a neutron star merger, you see a different kind of development. Okay. This is the same 4 trajectories, showing it for the beta decay rates. Again, you have a large number, depending on the astrophysical scenario, that you can access with existing facilities, and AFRIB will have a good chunk of it, but not if it's a cold wind and so on. This is a closer calculation plot for ruthenium-128 showing the beta decay rate change. Just wanted to give you an example. 0? Okay. So in the red here is the calculation where we've decreased the beta decay rate by a factor of 10, and blue is where we've increased the beta decay rate by 10. Obviously, we don't have the beta decay rate for ruthenium-128. And the F metric varies between 20 to 7.5, and then you can see the percent differences depending on what the situation is. I'll speed this up. Beta-delayed neutron emission probabilities for the 4 trajectories, neutron capture rates for the 4 trajectories, and again, another example of what happens with the F value for a neutron capture rate. In this case, the red is decreasing a neutron capture rate by a factor of 100. The blue is increasing it by a factor of 100 and the impact that it makes. So the F metric values are very different. And bringing us to where we are today. This plot in gray shows all of the masses that have been measured in the last AME 2012 evaluation. So we've not included the ones that they've made predictions for. And it's quite impressive, the results from RECAN, which were just published about a month ago, where they've measured the beta decay half-lives for all of these nuclei indicated by triangles here. And I only indicated, in making a plot like this, you get into a lot of controversy. But what I've shown here are the ones that people have managed to measure, not the ones they think they're going to measure, except for the FRIB line here. But you see the stars here have been measured at Caribou, at Argonne National Laboratory, and the blue dots are the ones that have been measured at ISAC at Triumph. So in terms of FRIB, that's the line, and then the color indications here in pink are the ones that have F values that are greater than 0.1. So we've indicated, yes, depending on the astrophysical scenario, we are going to be able to measure lots of nuclei that are important for our process, and some of the most important ones are indeed within the range that we can access. So I'll end there since our chair is getting a bit anxious in the front row here, but just want to summarize by saying that this is the most comprehensive sensitivity studies ever performed. I think we've been able to identify, depending on the astrophysical scenario, which nuclear properties play a bigger role, and hopefully with narrowing down some of the uncertainties on the nuclear physics side, we'll be able to clearly distinguish between favored scenarios for the astrophysics. So I'll just leave by saying that disentangling nuclear physics from the astrophysics uncertainties, we're making progress, but we're certainly not there yet. We certainly could use much better precision on nuclear models. So I'd like to thank you for your attention, and just to say that we are making a path. We don't know the answer yet, but we're getting there, and this work was done with a lot of others whose names are mentioned here. Thank you for your attention.
Okay, sure. When you started, you showed us the YE values, and the sites were very neutron rich. But when you look at the plots of the important nuclei with the wind-driven in particular, they're much less neutron rich. So that's apparently some process of the wind, the neutrino effect.
Yes.
Right? Could you comment on that?
Sure. The core collapse supernovae doesn't have the amount of neutrons that you need to make what we see. That means to make the R process all the way up to the uraniums and thoriums. It doesn't have it to date. The neutron star mergers certainly have the number of neutrons you need to do it, but the frequency or the time scale is not right. So neither site is perfect for now. But those are certainly issues on both sides. You need about 100 neutrons per seed nucleus in order to do the R process, or get out to the heavier R process nuclei.
So how considerable is the difference of your work calculation results with the waiting point approximation? And the second question, if you considered the cycle when fission of actinides brings the matter to the middle mass nuclei and it goes again, so similar to the C0 cycle in the sun, for instance.
Yes, absolutely. I mean, I didn't concentrate on that, but in the cold...
The first question about the waiting point approximation.
So do you want me to answer it, or...?
Yes.
Okay.
Two questions.
The waiting point approximation is equivalent to the hot wind high entropy calculation. So it's equivalent to that. You get the same results for that. The other question you mentioned with the fission recycling, that's only important in the neutron star merger scenario. And we do include that for the cases where it's applicable. So for the cold R process, even if you get up to the very actinide region, fission recycling is involved. So we do consider those.
But for the core collapse, there is so-called Panov peak. So if one considers this kind of cycle, it gives a peak also for the core collapse supernova.
For which?
For the core collapse supernova.
What does it give a peak for?
So that's a peak well in the middle mass numbers. It's predicted by Igor Panov.
Yeah, for the core collapse, where you have the cold wind scenario, where you're very far out. In fact, I think I have a plot I can show you here. Though this is for the neutron star merger flow. I don't think I have it here. Sorry, I thought I did. This is the nuclear flow for a neutron star merger, sort of snapshot at 100 milliseconds. When you run out of neutrons, basically, when the neutron to seed ratio is 1 and then the beta decay to stability, you need to have fission recycling here, as you do with the cold neutrino wind scenario.
Thank you. Regarding the astrophysical scenario, when people investigated gamma ray bursts, they found two distinct classes, one short time, the other long time. And they associate them with either neutron star mergers or neutron star black hole mergers. So this is clearly distinguished, and I wonder whether you have a chance eventually to distinguish these two classes also in the R process abundances.
I don't know the answer to that because this two-neutron star merger trajectories are from Yanka and company. I don't believe we have the neutron star black hole combination, so I don't know. Yes, for the future.
Yeah, Peter.
I have what I hope is a quick question. Is this working? You said you couldn't tell us the site of the art process. Can you exclude some site?
Not yet. That's what, actually, I sort of played a trick on you by not showing you the, let's see, let's do this. So these figures show the same sort of error probabilities on a neutron star merger and a hot R process. You see that the errors are reduced depending on which nuclei are engaged in the R process. So I think with better errors here, we can potentially distinguish these kind of scenarios. But this is done with half an MeV binding energy variation. You can even have a narrower band if we could get mass models, not only mass, of course, because the neutron star merger also involves other things to see better. But you'll see a much narrower band in such an uncertainty band. And then you'll be able to distinguish between the two. But not yet. Well, in this particular case, I mean, it looks bad, but it's just because of the fission recycling. In this particular case was not engaged. But if you do that, that just contributes down there. So it's not as bad as it looks there. Really, the issue is more here.
Okay, Patty.
Yeah, is it really surprising that most of the mass model or all the mass model that you use predict a similar group of nuclei that are important? Because after all the mass model must use very similar physics, otherwise they are all wrong. I mean, they will be not very correct, right? I mean, the fact that they're using the same physics, or hopefully the correct physics.
But
So
they're
can you
not.
just-
I mean, that's my point. That's why I showed this figure here. It's coming. This one. The models that I show here in green, red, and blue, they're very different physics. Very different physics input. And variations in what you would expect for mass excess values. This is a ratio on the order of factors of 2 in some cases. So the physics that's going in is very different. It's shocking that the outcome is the same. You're not convinced?
No, I think you have to maybe vary it more.
Okay.
Vary it more? Actually, yeah, this one was done 1, but we also did half, and we even did 100 keV. Then you see a huge difference in the abundance distributions, even at 100 keV.
So maybe we can discuss it later. We are already running a little late.
Okay.
So thanks a lot, Arnie.